Welcome to Data Science 1, Probability, Negative Binomial Experiments. Okay, some things we're going to need to know for this particular video. If you're not comfortable with these, you might want to go back and look at the previous videos. We need the multiplication rule, combinations, random variables, and probability distributions. Okay? Oh no, not more Bernoulli experiments. But yes, more Bernoulli experiments. Why? Because they're so easy, right? There's two outcomes and there's no in between. Makes life really simple and makes probability really easy as well. And if we ultimately design our experiments that we wish to make inference about on this type of experiment, then we already know how to analyze it. All right, so here's the idea of a negative binomial experiment. And it's similar to the geometric experiment, except that we're interested in X being the number of failures of independent Bernoulli trials before the kth success. If you remember from the geometric, we were stopping at the first success. Here, somebody might say, yeah, well, you went along and you only got to see one success. I would like more information about that before I make any conclusions about the probability of success, which is fair enough to say. So they would run the experiment until they had seen so many failures, which they pre-specified. So in this case, suppose the sample space is not as easy to write in this case. So we have, what are our options? We have SSS, that would terminate it if K was 3. FSSS, that would terminate it if K is 3. But SFSS also works. And SSFS works because there's 3 successes. And then we have FFSSS and then so on. And it's kind of complicated to keep track of all these. But we don't really have to think about it that way if we look at the number of failures. All we have to do is look in here. How many failures are in there? 0. How many failures in this one? 1, 1, 1, 2, 2, 2. Very easy to deal with instead of having to think about it this way. So that's why we like this thing called the negative binomial. And at this point, you're going, why is this a binomial experiment? It doesn't seem at all like a binomial experiment. And I'll show you why right here. So if we go along with let P be the probability of success, and of course then 1 minus P is the probability of failure. If you look at this formula right here, it looks awful close to the binomial experiment or the binomial distribution. You have something, choose something, 1 minus P to the X, P to the K. These look surprisingly similar, but they really are different because with the binomial, you have a fixed number of trials. Here, we're just going to keep going until we hit the number of successes that we picked ahead of time. So our density is the probability X equals little x. Well, there's going to be X failures, and there's going to be exactly K successes. So this part here makes sense. P to the K. There's K successes. They're independent. We can multiply them together. There are X failures. 1 minus P is the probability of a failure. Since there's X of them and they're independent, we can do 1 minus P to the X. Now, this is the bit that kind of confuses people, okay? But just think about it this way. I'm going to have the number of failures plus the number of successes is the total number of spaces that I have to put in my successes, right? But here's the kicker. I know the last one is not available. The last one has to be a success. That's why I subtract off the 1. All the other ones we can move things around, but that last one has to be a success. And X is the number of failures, right? So I have to pick out of those positions where I'm going to put the failures, the X failures. Okay, so this is pretty easy to deal with, but it accounts for looking at the places that you would put of this. Now, there are several formulations of this distribution, so be careful. If you look on Wikipedia, you might see something different than this. If you look in a textbook, you might see something different from this. This is the one I think that's the easiest to think about, so that's what we're going to stick with. All right, so let's look at an example. Fatima has taken a proficiency exam on a computer. The computer is designed to keep offering questions until the student misses 5 questions. Given that for each question, each has 4 choices, the questions are independent, what is the problem that Fatima will answer exactly 9 questions if she guesses at the answers? Okay, well, remember we have 5 questions that you're going to miss. So this is the K, okay? Then X here is the 9, wherever we hit 9, minus the 5. That's where this x equals 4 comes from, because these two need to add together to be 9. Okay, now this 4 choices goes into the probability. The probability you pick the right number is 1/4 if you're just randomly choosing. So the probability that x equals 4 is equal to, plug everything into the formula, distill it all down, plug it in your calculator and whatnot, and you will see that 0.0216 is the probability. She just randomly guessed, kept randomly guessing at the questions, that she would get exactly 9 questions that offered up to her. Because remember, she misses 5 of those, and she's randomly guessing at these. So anyway, this is a simple example of this. We'll look at more examples as we go along. Right now, we're just trying to introduce different distributions. So again, it's a Bernoulli experiment. Sample space is really large. Random variable is the number of failures until a success. Not a success, but the kth success. And we have the probability distribution, so we're good to go. Now we have another one to look at, and then we'll actually start using something. So let's find out what that another one is in the next video.